In the last two lectures, we've talked about cases where we have two variables. In this one, we're going to look at cases where we have a multinomial experiment. So what's a multinomial experiment? You may remember from back when we did distributions, a binomial distribution. And a binomial experiment was one in which we had two outcomes. So we had defective, not defective, yes, no, true, false, heads, tails, successes, failures. A multinomial is when you have multiple outcomes, so more than two specifically, okay? So what does that mean? We could have red, blue, yellow, doctor, lawyer, teacher, electrician, programmer, car, bus, train, or walk. So, what's your favorite color? What do you want to be when you get out of school? How do you get to your job or your school? What mode of transportation? So in each of these, we have multiple outcomes, okay? So that's what we're looking at here. We're looking at multinomial experiments. So red, blue, yellow would be an example of multiple outcomes. We said car, bus, train, walk. That would be an example of multiple outcomes. Another example we said would be, I want to train to be a doctor, a lawyer, a teacher, an electrician, or a programmer. These are all multinomial experiments. Now we've seen this before, okay? We saw it at the very, very beginning of the semester. We saw it when we were doing bar graphs, right? In bar graphs, we have multiple categories. And if you remember, each category was represented by a separate bar. And the height of the bar was the frequency. So this all stemmed from a frequency distribution. Well, that's what we're going to look at again. We're going to go way back to those frequency distributions. And the chi-square goodness of fit test, which you see written up at the top here, is used to test whether a frequency distribution that was collected from a sample fits an expected frequency distribution, what we think will happen. Okay, so we have our hypothesis, and then we have what happens in the sample, and we're saying, does what happens in the sample, is it a good prediction? Is it the same as the hypothesis? Okay, and this is typical. This is what we've done. We're saying, is what happens in the population, is it the same as what happens in the sample? Okay, that's what we've been doing with all of these hypothesis tests. Okay, so we're doing it exactly the same way, but instead of talking about a single mean or a single proportion, we're talking about this whole frequency distribution. So what we think will happen is the expected frequency, and what actually happened in the sample we called the observed frequency. Okay, so I'm going to put this in a different color because it's a description of what we will be doing in this lecture. So chi-square, it gets a different name because we're going to a whole new chart. So once again, we're going to be looking at a sample. So the frequencies obtained from a sample are our observed frequencies. We talked about the observed Y values in the last lecture, okay, right? When we were doing lines of regressions, we had the observed Y values, which is what we saw from the sample, and then we had the predicted Y values. Here, the predicted Y values are called expected, okay, expected frequencies or hypothesized frequencies. So how do we calculate these expected frequencies? Well, you're being given an expected percent, okay? So it might be that we think 24% of people prepare their taxes by going to an accountant. So that's an expected percent. We need an actual expected frequency, and we'll demonstrate this. The expected frequency is the percent or the probability that it's somebody who uses an accountant to prepare their taxes times the sample size. So we use the sample size because then we can compare it to the observed frequency. Okay, so E sub I is equal to N times P sub I, where N is the sample size. Okay, it's this, again, it's the same as the sample size so that we can compare it to the observed frequencies. If we used a different sample size to calculate the expected frequency, then we wouldn't be able to do that. Okay, and I represents each category. So what does that mean? Sorry. That means that P sub I is the assumed probability, the hypothesized probability for category I. Okay, so let's take an example. Okay, and we'll take the example of how taxes are prepared. And what we'll do is we'll give you the expected percent of people who prepare their taxes in different ways, and then we'll be calculating the expected frequency. Okay, so for example, we're going to look at the different ways that people prepare their taxes. And we're not going to look at the observed frequencies at this point. At this point, we're going to start by just looking at the expected frequencies and how to calculate them. So I'm going to tell you what the sample size is. So suppose that when we figured out our observed frequencies, our sample size was 300. That's a 3. Okay. So this is what you get. You have your different tax preparation methods. Then you have the percent of people, so expected percent. And this is what you're given. So you're given that we expect 24%. We're going to be adding another column in here. That's going to be the expected frequency. Okay. We expect that 24% of people prepare their taxes by bringing them to an accountant. Okay. We expect that 20% of people prepare their taxes by hand. They sit there with their forms and they calculate everything. We expect that 35% of people prepare their taxes using some sort of computer software. Okay. We expect that 6% have a family member or a friend prepare their taxes. And we expect that 15% use some sort of tax preparation service. Maybe they go to H&R Block and they have somebody there do their taxes, okay? So this is the expected percent, but now we need the expected frequency, okay? So how do we figure that out? Well, we're telling you that the sample size is 300. So we want to say, okay, well, if sample size is 300, how many people do we expect to have their taxes prepared by an accountant? Well, how do we do this? We take 300 and we multiply it by the probability of that category. So the probability of the category is the percent, but as a decimal, right? Because we have to turn it into a probability. So in this category, it's going to be 300 times 0.24. And if we calculate that, we get 72 people. So we expect out of 300 people, 72 will have their taxes prepared by an accountant. And we do this for each one. Here we're going to do 300 times 0.20 because that's what 20% is as a decimal. And we get 60. For the next one, 300 times 0.35. And we get 105 out of 300 people prepare their taxes using computer software. 300 times 0.06, we get 18. And 300 times 0.15, and we get that 45 people use the tax preparation service. Okay, now this is expected. This is our hypothesis. Okay, it's not what actually is. What actually is would be observed frequencies. I did not give that to you here. Okay, now in a regular problem you would get it, but here we're just calculating expected frequencies. Let's do another example. So again, in the next example, I'm going to give you expected percents, and we're going to calculate the expected frequency. So in this example, we're going to look at the number of doctor visits. For a U.S. adult in 1 year. Okay. Sample size. So again, we give it to you. Is 600. Okay. So again, it matches our sample size. Because this way we can compare the expected frequency to the observed frequency. Is the expected frequency greater than the observed frequency or less than the observed frequency? So let's give you some information. So we're going to give you the expected percent. The expected frequency is a number of adults. And that's what's not given to you. Okay. So I'm putting that in red. This is what we're calculating. So we have no doctor's visits. We have 1 to 3 doctor's visits during the year. We have 4 to 9. And we have 10 plus. Okay. Whoops, I did not mean to put that in red. I'm going to change it to black. And the reason I'm changing it to black is just so that you know what you're given versus what you're trying to find. So the doctor visits, the categories you're given. The expected percent you're given. The expected frequency is what you need to find. So that's why I'm putting it in red. Okay, so you're given this. The percent, we say 15.3% of adults don't go to the doctor at all in a year. 50.4% go to the doctor between 1 and 3 times. 22.8% go to the doctor between 4 and 9 times in a year. And 11.5% go to the doctor more than 10 times. Okay, so how do we calculate the expected frequency? Well, our sample size is 600. So we want to figure out what is 15%, 15.3% of 600. And if we calculate this, it's 92. And it's not an exact number, right? If you look at this on a calculator, when you calculate this, you don't get exactly 92. You get 91.8. So round to the nearest whole in this case, okay? For this one, you get 600 times 0.504, When you round to the nearest whole, that's 302. 600 times 0.228. Notice we're moving the decimal point 2 spaces to the left. We get 137. Sorry, I don't know what happened there. Sometimes it just puts in this random line. Okay, this is a 2 here. Then for the last one, we have 600 times 0.115. And there we get 69. Now your expected frequencies should add up to your sample size. So you should check that, okay? Check that 92 plus 302 plus 137 plus 69 is 600, and it is, okay? So this is one way to check. Okay, so this is how to calculate the expected frequency, but now the question is how do we know if the expected frequency matches the observed frequencies? Okay, it's like we said, it's a goodness of test. It's does the frequency distribution, the frequency distribution that we get from doing a sample, from asking questions of a sample, is that the same as the expected frequencies that we see here? Okay, and that's what we mean by performing a chi-square goodness of fit test. Now, not surprisingly, this is a hypothesis. So what a chi-square goodness of fit test is really a hypothesis test. Okay, so let's go through how we do this. And not surprisingly, it's very similar to all of the other hypothesis tests. Like I said, we just use a different chart. So a couple of things, okay? Before we write down all of the steps, there are some requirements, okay? So the first thing, each expected frequency must be greater than 5. So each expected frequency is your E sub I, right? E sub I is the expected frequency for each category. So greater than or equal to 5. Just like in our binomial experiments. Right? When we were doing hypothesis tests for proportions. Proportions are binomial experiments, and we said NP had to be greater than or equal to 5. Well, here we have multinomial experiments, and we're saying the same thing, right? NP is the expected frequency. It has to be greater than or equal to 5. And it is. All of these are greater than or equal to 5. In the one that we did before this, all of our expected frequencies were greater than or equal to 5. Okay. So that's the first thing. That's what we do to say, okay, well, we could actually do this hypothesis test. Okay, so, and I'll actually write this in, and you'll see in 1 second, but this is a hypothesis test, which means that the next step is to create our hypothesis. So just like before, we have a null hypothesis and we have a alternative hypothesis. And just like before, We're assuming that the null hypothesis is true. And at the end, we're concluding that either we're rejecting the null hypothesis or we're failing to reject the null hypothesis, which means if our claim is the null hypothesis, we're either rejecting it or failing to reject it. If our claim is our alternative hypothesis, we're either saying that there's enough evidence to support it or not enough evidence to support it, okay, depending on whether we reject the null hypothesis. So in this one, the null hypothesis and the alternative hypothesis are always the same, just like they were when we did our test for whether or not the correlation is significant, right? When we did that test, we said that if we accept the null hypothesis, if we fail to reject it, we talked about whether or not we had enough evidence. So we said sorry, I lost my chain of thought. We said if we reject the null hypothesis, then it is a significant correlation. And if we fail to reject the null hypothesis, then there is not a significant correlation. So the same thing is true here. It has to do with whether we believe that the expected distribution differs or not. Okay, so the null hypothesis is simply saying the expected distribution of whatever we're doing. So the expected distribution of the number of times U.S. adults see doctors is 15.3% go never, 50.4% go 1 to 3 times, 22.8% go 4 to 9 times, and 11.5% go more than 10 times. Okay, that's the null hypothesis. The alternative hypothesis is saying, nope, the distribution, so the actual distribution of the number of times U.S. adults go to see doctors differs from the expected distribution. And you'll see examples of us creating both the null hypothesis and the alternative hypothesis. So remember, chi-square test says this matches the actual distribution. Okay, so the null hypothesis says yes, it matches. The alternative hypothesis says nope, doesn't match. Okay. The third thing is that, again, we need degrees of freedom. And in this example, the degrees of freedom is k minus 1, where k is equal to the number of categories. And we use the chi-square distribution chart. So this is a new distribution chart that we have not seen before. Okay, let's take a look at that chart. So this is the chi-square distribution chart. So it's easy to use. It's just as easy as the t-distribution chart. Okay, you have your alpha, which is your level of significance. Okay, and then you have your degrees of freedom. So if you're talking about a level of significance of 0.1 and degrees of freedom of 4, you go over to 0.1 and you go down to 4. Okay, this is very simple to use. You're just looking at your alpha. You don't have to think about two-tailed, right-tailed. We don't have to think about those tests here. This is always, it's always going to be the same for the chi-square distributions that we use. We're always using right-tailed tests. So we look at the point. We're going to be looking at 0.1, 0.05, 0.01, sometimes 0.025 or 0.005. But most of the time 0.1, 0.05, and 0.01 like we happen. And all you do is you go to the alpha that you need, and then you go down to the degrees of freedom. Okay, so it works just like the t-distribution chart. So we need to figure out the degrees of freedom though. So in this case, we have 4 categories. So our degrees of freedom would be 3. Now we don't know what our alpha is, but if, for example, our alpha were, if our alpha were 0.1, degree level of freedom of 3, 6.251. If it were 0.01, then we would be using 11.345. Okay, so those are the numbers that we're using. That is to create that rejection region. Okay, so once again, the hypothesis test, almost all of them that we have done has been using a rejection region. So we're using a rejection region again. Okay, so these are the major things for the hypothesis. The very last thing is your test statistic, right? So we need to calculate the test statistic. So the test statistic is chi-squared, okay? So what does that look like? It looks like an X, but it's like this pretty X. Okay, we make these really nice curlicues. Okay, so it's chi-squared. And what is this equal to? This is the tedious part of this process because this is what we actually need to calculate. So it's the observed frequencies minus each of the expected frequencies. We square that. We divide each of those by the expected frequency for that category, and then we take the sum. Okay, so this is the part that you're going to see takes us a while, but this is straightforward. It's exactly the same thing that we've done all along. So how do we do this? Exactly the same way. First, we need to verify that it's a random sample. You can see how important random samples are. And that all E sub I, so all of your expected frequencies are greater than or equal to 5. Okay, and you're going to have to do that. You're going to be doing that work anyway. You're not doing extra work because you have to calculate the expected frequencies. Then you need to state your hypotheses and identify your claim. You're going to specify the level of significance and the degrees of freedom. Notice these steps are exactly the same. Level of significance is given to you, or it's something that you decide. If you're doing these experiments, all of these experiments are things that, problems that we're giving you. But if you were to actually do this out in the world, you would be collecting your own sample and you would be deciding on your own level of significance. Then you're going to figure out your rejection region. And that's where you have to go to the chi-square distribution chart. Right? That's your, we call those your critical values. That's where you're finding your chi-squared, but it's your critical value. It's chi-squared 0, right? Then you're going to find your test statistic. And finally, you make a decision. Do you reject the null hypothesis or fail to reject the null hypothesis? And make a conclusion about the claim. So does that mean that your expected distribution matches or it does not match? Okay. Okay, I promise it really doesn't look so slanted on my paper. I don't know why it comes out so slanted. Okay, so let's take, we're going to do 3 examples where we go through this whole process, all of the calculations. And again, this is the type of thing where the calculations, particularly to calculate chi-squared, okay, not from the distribution chart, but to find the test statistic, that is a very time-consuming, tedious process, and a lot of times you would use the actual you would use technology to do it. Okay, so we're going to go and we're going to use what we calculated before. We're going to use this example as our first example. Okay, and we calculated all of the expected frequencies. So I'm going to create a new table with what we calculated. I'm going to put the expected frequency in red so that you know that we already calculated it. Okay, and I'm going to add in the observed frequencies. And the observed frequencies I'm going to be putting in black because you would have already received that. Okay, those would be given to you in any problem that you do. Typically, you would not be given an expected frequency this way. You would have to add it into the chart after observed frequency, or it would be given to you. Sometimes you'll be given 2 separate charts where you get tax preparation method, expected percent of people, and then another one that has tax preparation method and then observed frequency. And you would have a whole, you would have to add to the different charts. Okay. So the expected frequency, we already calculated it, so I'm not going to calculate it again. I'm just going to use what we found. So we had accountant, we had by hand, we had computer software. I'm just going to write computer here. We had a friend or family member. And because we had this chart already, I think I'm safe to write service. as opposed to tax preparation service. Okay, just to review, our expected percent was 24% for accountant, then 20%, 35%, 6%, and 15%. The observed frequencies, when we did the sample and we asked the people in the sample, was 63, 40, 115. So this is new information I'm giving it to you. 29 and 53. This is a 3. Okay. And we already calculated the expected frequencies based on the sample size. Okay. The expected frequencies based on the sample size were 72, 60, 105, 18, and 45. And I just realized here that I never actually said what the example was. So let me write that out, and it should go above. So the example for this chart, we're saying that, because I have to give you the claim, right? So a retail trade association claims that tax preparation methods are distributed with the percents shown. Okay, the percents shown. A tax preparation company selects 300 adults. So remember, when we calculated the expected frequency, we did it based on a sample size of 300. So this still holds. And this number did not come out. That's an 105. So they select 300 adults at random, so random sample. And it asks how they prepare their taxes. Okay, now the results are the observed frequencies. The results from the sample are always the reserved frequencies, the observed frequencies. So we're going to say at alpha equals 0.01, test the association's claim. That should be in blue. I apologize. I'm not going to rewrite it. I'm sorry, it's not in blue. Okay, so let's do the problem. First thing that we do is we verify all expected frequencies are greater than 5. And that it's a random sample. It is a random sample. All E sub I are greater than or equal to 5, right? All of these are greater than or equal to 5. These are the ones that we're looking at. Second thing that we have to do. We have to create our hypotheses. So this is what our hypotheses look like, okay? And I'm going to be honest, it's a pain to write them. The expected distribution of the way people prepare taxes, you're essentially rewriting the chart. Is not taxes, that would not make sense. %24 by accountant. %20 by hand. 35% by computer. Imagine if you had 10 categories. 6% by friend or family. And 15% by service. This is your claim. That's the claim of, I don't know why it disappeared. Okay, so 6% by friend family, 15% by service. This is your claim, okay? Okay, the alternative hypothesis, much easier to write. The alternative hypothesis, which is always the same. The only thing that's going to change here is what that expected distribution represents and which is your claim, okay? And the claim is always stated in the problem itself. So here, the alternative hypothesis is the distribution of the way people prepare their taxes I don't know why I keep writing taxis. We're not talking about taxis. Differs from the expected distribution. So the only thing that changes as you write your alternative hypothesis is this of the way people prepare their taxes, of the number of doctor's visits per year, okay? That's what's going to change. But the distribution differs from the expected distribution. That's always the same, okay? And sometimes the alternative hypothesis is your claim. Okay, next. Here, our level of significance we said is alpha equals 0.01. And our degrees of freedom is k minus 1. In this case, we had 5 categories. So our degrees of freedom is 4. Now we need our rejection region. So remember our rejection region? That's the sub-zero, is going to be based on the x sub 0 squared, okay, the chi-squared. That means that we go to our chart. We have a 0.01 level of significance, and degrees of freedom is 4. So the number that we're looking at is 13.277. So that's our chi-squared. Okay, which means that our rejection region is that chi-squared is always, this is always the way that you write your rejection region, that it's greater than chi sub 0 squared. Okay, so this is our rejection region. And now we have to calculate chi squared. So this is the part that we really don't like so much. Okay, and we don't like it not because it's hard. This is just addition and subtraction. We just don't like it because it's tedious. Okay, it's time consuming. So we're going to recreate the chart, and the first 2 columns of the chart are identical to the chart that we already have. Okay, and then the rest of the columns are going to be used to calculate the chi-squared. So when we calculate the chi-square, remember what that is. That's the sum of our observed frequencies minus our expected frequency over the expected frequency for each category. Okay, so we have to do this for each category and then add them all together at the end. Okay, so we're going to recreate the chart. We're going to have our O, that's our observed frequency. Our E, that's our expected frequency. Then we're going to subtract them. We're going to square it. And then we're going to do the O minus E squared over E. These are our different columns. So let's calculate. So we have by accountant, by hand, by computer. I'm just going to put by friend. And I'm just going to put by service. Okay. First 2 columns are exactly the same. We're taking our O from the observed frequencies here. These are our O's. We're taking our E from the expected frequency here. These are our E's. That's 115. Tops of the 5s don't come out. So we're just filling in those 2 columns. So just make sure that they're going into the right column. So we have 63, 40, 115, 29, and 53. Okay. Then our expected frequencies were 72, 60, 105, 18, and 45. Then we have our O minus our E. So this would be 63 minus 72. So we get -9. We're doing that for every one. 40 minus 60 is -20. 115 minus 105 is 10. 29 minus 18 is 11. And 63 minus 45 is 8. Now we do O minus E squared. Okay, when you do this, you should get a positive number. That -9 has to go in parentheses, okay? Has to go in parentheses. These are all positive. So we get 81. I'll do this again. -20 goes in parentheses. So we get 400. For this one, we get 100. Then 121. And then 64. So we're taking this column here and we're squaring it. Now we're going to take the O minus E squared column and we're going to divide it by the E. So this would be 81 over 72. Don't round too much, okay? Go to the third decimal place here. We get 1.125. Here, it would be 400 divided by 60, which gives us 6.667. 100 divided by 105 gives us 0.952. 121 divided by 18, 6.722. And then 64 divided by 45 gives us 1.422. So chi-squared is going to be 1.125 plus 6.667 plus 0.952 plus 6.722 plus 1.422. And what we get here is 16.888. Now we're going to see if it's in the rejection region. So it is. 16.888 is greater than 13.277. So we're in the rejection region. Meaning we reject the null hypothesis. And because the null hypothesis was the claim, we're rejecting the claim. Okay. What does that mean? That means the expected distribution differs from the actual distribution. Okay, let's take another one. You can see that these are only long to do because we have to calculate that chi-square. So a sociologist claims that the age distribution of residents of a city is different from the distribution 10 years ago. So you randomly select 40 residents. Sorry, 400 residents. And record the age of each. So the results are shown below. I'm going to give you a table. So at alpha equals 0.05, we're going to test whether the distribution has changed. So keep in mind what that means here. This means that the expected distribution is the distribution from 10 years ago. Okay? So we have our ages. We have the expected distribution. So I'm not going to label it expected distribution. I'm going to label it previous or distribution from 10 years ago. These are your survey results. So this is what's given to you. And we have more categories here. We have age 0 to 9, 10 to 19, 20 to 29, 30 to 39, 40 to 49, 50 to 59, 60 to 69, and 70 plus. So the previous distribution from 10 years ago is 16% of the population was between 0 and 9. 20% of the population was between 10 and 19. 8% between 20 and 29. 14% between 30 and 39. This is a 9. 15% between 40 and 49. 12% between 50 and 59. 10% between 60 and 69. And finally 5% 50 plus, 70 plus. Okay, now the survey results are 76, 84, 30, 60, 54, 40, 42, and 14. Okay, well, the first thing that we need to do is we need to verify that the expected frequencies are greater than or equal to 5. So we have to calculate those expected frequencies. So I'm going to put that calculation over to the side over here, okay? So this is something that we're adding. How do we figure out the expected frequency? We take the sample size. The sample size is 400. And we multiply by the percent. So we're multiplying by 0.16. And we get 64 here. That's greater than or equal to 5. So we're okay there. 400 times 0.20. We're okay here too. We get 80. 400 times 0.08. Again, we're okay. We get 32. 400 times 0.14. We get 56. 400 times 0.15. We get 60. 400 times 0.12. We get 48. 400 times 0.10. We get 40. And 400 times 0.05. We get 20. So all of our expected frequencies are greater than or equal to 5. This is a 48, not a 45. Okay. Now we're going to need these. So it's good that we calculated them because we need them to calculate chi-squared. Okay. So let's just go through our checklist. So 1, it is a random sample. It says we randomly select. Check. All of our E sub I are greater than or equal to 5. Yes. Check. We verified. Okay. Now we need to do our null hypothesis and our alternative hypothesis. Okay. Null hypothesis. We love it. Sorry, I should write H sub 0. H sub 0. The expected distribution of residence ages is 16% for 0 to 9, 20% for 10 to 19, 8% for 20 to 29, 14% for 30 to 39, 15% for 40 to 49, 12% for 50 to 59, 10% for 60 to 69, and 5% for 70 plus. Our null hypothesis, our alternative hypothesis. This says the distributions of residence ages today differs from the distribution 10 years ago. This is the claim. Okay, the expected distribution is the distribution from 10 years ago. Okay, so we are still saying that the distribution differs from the expected distribution. Okay, alpha is equal to 0.05, and the degrees of freedom is equal to k minus 1. K this time is 8. So that means that chi squared sub 0 is equal to, we're going to go to 0.057 in our chart. So here's 0.05 and here's 7. So we're looking at 14.067. Okay, that's our chi squared sub 0. And what does that mean? That means that our rejection region is anything that's greater, any chi-square that's greater than 14.067. So now comes our favorite part. We get to calculate chi-square. So remember, chi-square is equal to the sum of that last column, where we take the observed frequency minus the expected frequency square, and we divide by the expected. So we have our categories. We have our ages. We have our observed frequency, which comes from the chart that we already have. Our expected frequency, which comes from the chart that we already have. Our observed minus our expected. Our observed minus our expected squared. And then our observed minus expected squared over the expected. So we have 0 to 9, 10 to 19, 20 to 29, these were our categories, 30 to 39, 40 to 49, 50 to 59, 60 to 69, and 70 plus. And remember, first two columns come straight from what we have before, and this is why we calculated our expected frequencies, other than just to determine that it was greater than or equal to 5. We needed to calculate them all anyway, so we haven't wasted any time. So the O and the E come straight from this chart right here. Here's the O. The surveyed results are the O. And here's the E. The E is what we calculated. Okay, that's why originally we said the expected frequencies or the hypothesized frequencies are what we calculate. So if we just take from that chart, this was 76, 84, 30, 60, 54, 40, 42, and 14. And the expecteds were 64, 80, 32, 56, 60, 48, 40, and 20. The O minus E says subtract these two columns. So you're doing 76 minus 64. I do it for like the first two rows so that you can see what's going on, and then I just stop. So we get 12, 84 minus 80. We get 4. Here we get negative 2, 4, negative 6, negative 8. This is a 2 here. Again, it comes out on the paper and then it doesn't come out on screen, so my 2's don't really look like that. Negative 8, 2, and negative 6. Okay, now we square it. So this would be 12 squared. 12 squared is 144. This is 16. This is negative 2. Don't forget to put it in parentheses. You should always have a positive number here. We get 4, 16, positive 36, positive 64, 4, and positive 36. Okay. Now we take the O minus E, all of the numbers in this column, and we divide by the numbers in this column. Okay. So it's 14 over 64. That gives us 2.25. This one, it would be 16 over 80. That gives us 0.2. It's 0.200. We're doing so much writing that I'm not writing out the 00. I'm trusting you to understand that. We get 0.125. We get 0.286. 0.600. 1.333. Notice I'm going 3 decimal places. 0.100. 1.8. Okay. And all we do to calculate chi-squared then is we take the sum of this column. So we're adding all of these numbers together. So this is 2.25 plus 0.2 plus 0.125 plus 0.286 plus 0.6 plus 1.333 plus 0.1 plus 1.8. And this gives us 6.694. Now 6.694, so this is the 6th step. 6.694 is not greater than, okay, 14.067. Chi-squared is outside the rejection region. So if it's outside the rejection region, then we fail to reject. Now, what does this mean? Keep in mind, the claim was the alternative hypothesis. The claim was that the regions differed. And we're saying there's not enough evidence to support that claim. We're failing to reject the null hypothesis. So there's not enough evidence to support the claim that at a 5% level of significance, the distribution of ages today differs from the distribution of ages 10 years ago. It's not saying that they're wrong. It's just saying there's not enough evidence. And it's important to understand that it's at a 5% level of significance. This might be different if it were a 1% level of significance. just to give you an idea, we said that the degrees of freedom was 7 here. And because there are 8 categories, so the degrees of freedom is 7. And we said that the level of significance is 0.05. Let's change this. Let's say we said degrees of level is 7. We had a 14.067. Okay. If we had a level of significance of 0.10, this number gets smaller. Now it turns out that it doesn't matter which it is, right? It's always falling under. It's never in that rejection region if we're looking at the 0.1, 0.05, and 0.01. But notice that the numbers are different. So that's why it's important to say at a 5% level of significance, because it might be different at a 1% level of significance or 10% level of significance. Okay? Okay. Let's do one last one. And then we're done. And I encourage you to pause the video and do this one on your own. And then you can do it on your own, and then you can follow the video and see if you did it correctly. Okay. So this one is slightly different in the sense that it says the expected distribution is uniform. Okay. And uniform, the only difference is that it means that every expected frequency is the same. Okay. So a researcher claims the number of different colored candies in bags of M&Ms is uniformly distributed. So we don't have to give you the percents, you can find the percents, okay? And we'll talk about that in a second. So to test this claim, you randomly select a bag that contains 500 M&Ms. So the results are shown in the table below. And we're asking at a level of significance of 0.10, so 10%. We're going to test the researcher's claim. So here's what you're given. You're given the color. That's your category. And you're given the observed frequency. So our colors are brown, yellow, red, blue, orange, and green. And your observed frequencies are 80, 95, 88, 83, 76, and 78. Okay. Now you have to calculate the expected frequencies. Now here's the thing, right? They don't tell you. You don't get a chart with the expected frequencies like we did. So what do we have to do? This is telling us the expected frequency is the same for every category. Okay, so uniformly distributed means the expected frequency is the same, uniform, so every expected frequency is equal to the sample size divided by the number of categories. We're just dividing the whole 500 group into 7 groups. The whole 500 M&Ms, we're dividing it evenly into 7 groups. And 500 over 7 gives you 83.33. And you can use the decimal. So all of these are 83.33. And if you add it all up, you get 500. So it's a nice, fast calculation. That's the only difference when it's uniformly distributed. Okay. Okay. So let's go through and do our hypothesis test. So first, it is a random sample. It says you randomly select. All of our E sub I are the same. They're all 83.33, so they're all greater than or equal to 5. Yes. Okay. H sub 0 is much nicer to write here. The expected distribution of colors is uniform with each color having 16.7%. Okay, how did we find 16.7? We just did I didn't mean 16.7. I'm just going to say the expected distribution of colors is uniform. That's all that you have to say. And H sub A is the distribution of colors. In an M&M bag differs from the expected distribution. You could say it's not uniform. Each color has, you could put in with each color having 16.7%. Essentially, how we did 16.7 is we just did the opposite. We did 83.33 and we divided by 500. And I didn't mean to do, sorry, I meant 500 divided by 6. I put divided by 7. We have 6 categories. My mistake. That's why I was getting confused, because I was trying to calculate the percentage and I was getting weird answers, but that's why. So it's 500 divided by 6. This is 500 divided by 6. Okay, sorry about that. So 500 divided by 6 is 83.33. We have 6 categories here. That's why I was getting confused. So the expected distribution of colors is uniform. You can either do 100% divided by 6, or you can do 83.33 divided by 500, and that'll give you the percent for each color. Okay, you can say the expected distribution of colors is uniform. That's fine. Which is the claim? The claim is that it is uniform, right? Researcher claims the number of different color candy is uniformly distributed. So this is your claim. Okay. Okay. Then we have part 3. Part 3 says alpha is equal to 0.10, and our degrees of freedom is k minus 1. K is equal to 6. 6 minus 1 is 5. So our rejection region, we have to go to our chart to find chi-squared sub 0. So degrees of freedom is 5. Level of significance is 0.10. Here's 0.10. Degrees of freedom is 5. Our chi-squared, our critical value, is 9.236. So our rejection region is chi-squared is greater than 9.236. Now we get to the fun part. We calculate chi-squared. So again, notice I put it here every time. It's our observed minus our expected frequency squared over the expected frequency. Okay, we create our chart. So we have our color. We had brown, yellow, red, blue, orange, and green. We have our observed frequency, our expected frequency, the observed minus the expected, the observed minus the expected squared. And then the observed minus the expected squared over the expected. And we just take the sum of that last column. So this comes from the chart before, 80, 95, 88, 83, 76, 78. Those were given to us. Okay. The expected frequency we found to be 83.33. We took 500 divided by 6 so that those 500 M&Ms were evenly distributed into our 6 categories. And again, we can use a decimal. Okay. It is okay for our expected to be a decimal. If it doesn't have to be, then round. But here, it doesn't hurt for it to be a decimal. We're not talking about people. We're talking about M&Ms. Okay. These are all 3s. Remember, the 3s sometimes come out weird. Okay. So we're doing the second column minus the third, the 80 minus 83.33. Okay. That gives us negative 3.33. And we have 11.67. Uh, 4.67. Negative 0.33. Negative 7.33. And negative 5.33. Okay. Then we're going to square all of these. So remember, when you square, your negatives have to be in parentheses. Make sure you do that when you plug it in. Okay? So here we get 11.0889. It ends at the 889. So that's why I'm rounding all the way out to 4 decimal places, because there's no reason to round if we have exactly 4 places. Okay? We get 136.1889, 21.8089, 0.1089, 53.7829, and 28.4089. Okay. Now we do the 11.0889 divided by 83.33. Okay, so we're dividing. We get 0.133 here. Here we get 1.634, 0.262, 0.001, 0.645, and 0.341. So, our chi-squared, we just take the sum of that last column. We're adding together all of those numbers. That's what the sigma means. And we get 3.016. I put plus, I meant equals. Okay, so what does this mean? 3.016 is not greater than. It's not greater than 9.236. Chi-squared is outside the rejection region. So, what is our decision? The decision is we fail to reject the null hypothesis. What does this mean? There is not enough evidence Sorry, hang on 1 second. What I wrote in my notes is different than there is enough. There is not enough evidence to reject the researcher's claim. That the number of M&Ms is uniformly distributed. Okay, so remember the researcher's claim is the null hypothesis. So the null hypothesis is saying that the expected distribution is uniform. We're failing to reject that. So we're saying that there's not enough evidence to reject the claim. We're not saying that the researcher is correct. We can only say that if it's the alternative hypothesis, right? Remember that. The alternative hypothesis is the only one that can be supported. Here, we're saying there's not enough evidence to say that the researcher is incorrect. Okay? And this is the chi-square goodness of fit test. That's it. So it's very similar to everything that we've been doing. We just use a different chart. We have to go through and we have to calculate chi-squared, which is a little frustrating because it's tedious. But otherwise, that's it. Okay? And there will be one more video on this type of stuff, okay, using chi-square again.